Principal Component Analysis, abbreviated as PCA, and Exploratory Factor Analysis, abbreviated as EFA, are both statistical methods that can be used to analyze data extracted from a questionnaire or a survey, and the responses from the participant is recorded and scored based on Likert Scale. Principal Components Analysis, abbreviated PCA, for analyzing data extracted from a questionnaire or a survey. In this presentation, description of the PCA will be provided, and the common uses of the PCA will be mentioned, and the assumptions that have to be fulfilled before performing the PCA will be listed, and a short description how to input the data into one of the statistical software, and finally how to interpret an output from a PCA. Principal component analysis is a multivariate statistical techniques or a method that deals with data that consist of multiple variables or multiple items. It is an unsupervised statistical method. The objective of performing PCA is to reduce the number of variables in a data set. So it is dimensionality reduction method. It aims to reduce larger number of variables that is extracted from a questionnaire or a survey. Variables are items or questions. The objective is to reduce this large number of variables into a smaller number of variables that are, or a smaller number of variables grouped together, and these groups are called principal components. So the objective from performing the PCA is to reduce the number of variables and arrange these variables into groups called principal components. These components explain most of the variance in the original variables or data. Items within these components or variables or questions are correlated. The overall objective from performing PCA is to have a large number of items or variables. Try to reduce that number by grouping those items or variables into components. These components or variables within these components are correlated to each other. So what are the common uses of PCA? When a researcher starts to design a new questionnaire or an instrument or a scale, then a PCA is a useful statistical method. The objective of performing that method is to check if all or some of the items load into construct. If some of the variables are not sufficiently representative of the construct or the section within the survey or the instrument or the questionnaire, then remove those variables from the measurement scale. So PCA can be used to when designing a new questionnaire to check which items loads into certain sections or construct within a questionnaire, and those that they do not load to this construct, or they do not correlate with the variable within that construct, then remove that item or variable. The second use of PCA is to reduce the number of variables in a construct. So it is called construct PCA. If a construct consists of, let's say, up to 12 variables, then PCA can be performed to find out what variables within that construct, which is part of the questionnaire, that are highly correlated and represent the construct. The third use of the PCA is to shorten questions to be included in the questionnaire. Shorten these items or questions or variables into fewer items. So another objective is reduction. So if more than one item measuring same construct, then remove that item. And that will help to design a scale or an instrument that can be accomplished and completed by participant. So what are the assumptions that have to be fulfilled before performing PCA? The first assumption is that multiple variables are measured at a continuous level or ordinal. So the data or the responses collected from participant completing the questionnaire, it can be an ordinal based on 5 Likert scale from 1 to 5, or 7 or 9, and so on, or the responses can be a continuous variable. So there should be a linear relationship between all variables if they are continuous. PCA is based on Pearson correlation coefficient. The method also can be used for ordinal data such as Likert scale. Linearity can be tested using a matrix scatter plot. The second assumption is sampling adequacy. There have to be enough number of participants. There have to be 5 to 10 participants per question or per items as a minimum sample size. Using rule of thumb, 10 participants per question can be considered. And the way to check, or the method to check whether there is a sampling adequacy, is to perform a Kaiser-Meyer-Olkin sampling adequacy that will measure the sampling adequacy for all overall data sets. The third assumption is that the data should be suitable for data reduction, sufficient correlation between variables to reduce variable to a smaller set of components. Though there should be a correlation between items, that correlation has to be within a certain values from 0.3 to 0.8. The Parlet test of sphericity can be performed to test this assumption. The fourth assumption is that there is no significant outliers, and the fifth assumption is independent variables are correlated to each other. Another assumption is that principal components are assumed to be independent of each other. And finally, there should be a homoscedasticity. in which the variance of the data is constant across all level of the independent variables. In this slide, a print screen from a SPSS software has been inserted here. When performing PCA in SPSS, the following boxes need to be ticked. First of all, the correlation matrix, tick for the coefficient for correlation and the significance level for correlation, the determinant, which is an important values for testing the data and whether it is enough to be used for performing PCA, and also tick for the KMO and a partlet test of sphericity for sampling adequacy. The next slide gives options for selecting the method for analysis, which is the principal component analysis, and the eigenvalue is selected to be greater than 1. For performing the PCA, the method for rotation has to be decided in advance. There are two types of rotation. That depend on the variable, whether they are correlated. If the variables are correlated, then the direct oblimin will be used, or the Promax. When the variable are not correlated, then the method to use for rotation is orthogonal, and there are several methods: Varimax, Equamax, and Quatrimax. The output that will be generated from the PCA analysis, there should be important things to look for. There is no missing scores. To check for the correlation coefficient, which is the R, the Pearson correlation coefficient, the value for determinants, and the KMO and partlet test for sample adequacy and sphericity, the setting for the eigenvalues, the total variance, the Scree plot, the values for communalities, and the rotated matrix, with finally the table for the component transformation matrix. So this is a table extracted from a PCA analysis in which a correlation matrix has been generated for 9 items, item number 1 to 9, and the correlation between pairs of these pairwise of these items is given here, with statistically significant values shown here. And as shown here, that there is a perfect correlation between item 1 and item 1. And with item 1 and 2, the value is 0.65, and with item 5 and 1, it is 0.02. For the correlation values need to be, which is the R, need to be less than 0.8 and greater than minus 0.8. And the determinant has to be greater than 0.40 and 1. The next slide shows an output for the KMO and Bartlett test. The value need to be for sampling adequacy to be greater than 0.5, and ideally anything greater than 0.5 will be acceptable, but the higher the better. The p-value should be less than 0.05, and for the eigens values, when performing the PCA, the eigenvalues set out as greater than 1. So what does this eigenvalues mean? It represents the variance explained by each principal component. Higher the eigenvalues, the more variance is explained by the principal component. Here is a table extracted from a PCA analysis, as shown here, the total variance explained. There are here 8 items, and as shown in the section here, extraction method, principal component analysis, there are 8 items, and those items have been grouped into 3 major components: component 1, 2, and 3. Component 1 explains 27.3% of variance. The second component explains 25.7%. The third is 19.1%. The 3 component explains 72.2% of the variance. The next slide shows the Scree plot. Scree plot assists in determining the appropriate number of principal components to retain or to obtain from the analysis. It is used to visualize the eigenvalues and identify the point at which the curve levels off, suggesting that the optimal number of components to retain. Here in this graph, it shows that on the x-axis is the component number, on the y-axis is the eigenvalue. The cut point for the eigenvalue is 1, and there are 3 major components, 1, 2, and 3. The next slide describes a terminology called communalities, which is a table generated from the PCA analysis. Communality is the proportion of variance in each variable that is retained in the principal component. So the value for the communality ranges from 0 to 1, as shown here in the table. The first item has a communality value of 0.8, the second 0.7, and so on. The next slide describes factor loading. Factor loading is a measure indicates the strength and the direction of the relationship between variables and principal component. The higher the factor loading, the stronger the relationship. Factor loading is a coefficient, and the cut for factor loading as a rule of thumb is 0.3. Some people use 0.4, and some people become more stringent and use 0.45. So aim for a high value, which is 0.9. As shown here in the table extracted from a principal component analysis using a Varimax method for rotation, these 9 items has been grouped into 3 components, component 1, 2, and 3, as shown in this rotated component matrix. The first component have 3 items. These 3 items, item 4, 6, and 5, loads together on that component, and the loading factor score is 0.88, 0.7, and 0.7. So those 3 variables loads into that component. For the second component, there are 3 items. Item 1, 2, and 3 loads into the component 2, and the value for the factor loading is 0.9, 0.8, and 0.79. And finally, the third component have 3 items loaded into it. Item 7, 8, and 9. With the first one is 0.89, 0.7, and 0.65. All these 3 items load into the component principal component 3. So the overall analysis from the PCA has managed to group these 9 items into 3 components. Another output that can be generated post PCA is the component transformation matrix. The component transformation matrix will look at the correlation between component number 1 correlation with 1, and 1 with 2, and 1 with 3. So if the components correlate to each other, then this will help in determining the rotation method. then use oblique rotation, whether it's direct, oblimin, or Promax. When the components are not correlated, then use orthogonal rotation, such as Varimax, Equamax, and so on. And how do we determine the cutoff point for correlation or no correlation? A value of correlation between two components of greater than 0.32 indicates correlation between the components. Exploratory factor analysis, abbreviated as EFA, for analysis of data that is taken from a questionnaire or a survey. EFA is called also principal factor analysis, PFA, or principal axis factoring, PAF. PCA is the first phase of EFA. So when you have a data, the first step to do is to do principal component analysis. Then EFA can be done. EFA is a multivariate statistical method, a method that analyzes data that consist of multiple variables, few variables. It is commonly used when developing a questionnaire or a scale or an instrument in which there are multiple questions or items in the questionnaire, and each item or question represent a variable, and then the EFA is the method to use for the analysis of these multiple variables. The EFA is a statistical method used to uncover the underlying structure of a large set of variables. When there are large number of items or questions, then EFA will try to discover the underlying structure for these items, whether they can be grouped and loaded into a specific construct or a factor. It aims to identify a set of latent construct that underlying the measured variables, whether the group of variables measure certain construct or factor. EFA is an exploratory method that will explore whether large number of measured variable or observed variable related to a small number of unobserved factors. It aims to identify the underlying relationship between measured variable, try to find out whether there is a correlation between variables. It assumes no prior relationship among factors, so there is no correlation between factors, but there might be a correlation between certain items that might load or measure a specific construct or factor. So the EFA will determine factors that explain common variance, which is correlation, of a set of variables. It helps to understand how many factors can be present in the data. So it can section the data or the variable into groups, and those groups are called factors. It helps to identify underlying factors among survey questions, items, variables, the same terminology. The next step, once the EFA is done, is to perform confirmatory factor analysis. So what are the assumptions that have to be fulfilled before performing this statistical method? First assumption is that there should be adequate number of participants. Sample size have to be adequate, and the participant has to be greater than 150 individuals. More than 150 cases or individual or participant. At least there should be 20 participants per items or per variable or per question. One of the statistical methods that can be performed to find out whether there is adequacy in the sample size is to use the statistical method for Kaiser-Meyer-Olkin method. It will be given a value. Any value closer to 1 indicates better sampling adequacy. The second assumptions that have to be fulfilled is the eligibility of correlation matrix for factorization. The third assumption is linearity. There should be a relationship among variables, and those relationships are linear. So observed variables are related to the underlying factor in a linear manner. The fourth assumption, there is no perfect multicollinearity among variables. So variables, they should not have a high value of correlation or relationship. The fifth assumption is the normality. Though EFA is robust to violation of normality, variables should be approximately normally distributed, and if variables are not normal, then transformation for the data can be performed. The sixth assumption is the interval or ratio level of data. The data should be interval or ratio. For ordinal data, there should be more than 5 categories, and for categorical variable, then the best option is to go for categorical factor analysis. The seventh assumption is the homoscedasticity, which is equal variances. The variances of the observed variable roughly equal across all levels of underlying factors. The eighth assumption is that there is no outliers. Outliers are extreme high or low values within the data. The ninth assumption is that EFA assumes that the observed variables are influenced by two things. The first one is the common factor. The second one is the unique factors. Common factors are shared variance among variables, and unique factors are specific variance unique to each variable. And number 10 is the independence of factors. The EFA assumes that factors extracted are uncorrelated. If the factors are expected to be correlated, then confirmatory factor analysis can be used. Before performing the EFA, the factor rotation method has to be determined. Decide on appropriate rotation method and then run the analysis. There are two types of rotation. When the factors are anticipated factors are correlated, then go for oblique method. Oblique method can be a direct oblimin or Promax. When the factors are not related, then orthogonal rotation method can be used. There are subclasses for it: Varimax, Equamax, and Quatrimax. When performing the EFA on a data, a correlation matrix will be produced, and the items within this matrix all should be analyzed via bivariate correlation matrix. The value for the correlation coefficient, which is R, should be between less than 0.8 and greater than minus 0.8. Higher correlation coefficient values greater than 0.8 indicate multicollinearity. In this situation, the item or items have to be removed. So remove one pair of items with bivariate correlation coefficient score greater than 0.8. When the R value is less than 0.3 or greater than minus 0.3, then omit that item from the analysis. There is also another value determinant, which is called the determinant of the correlation matrix. So here is a output for the correlation matrix performed using EFA on 6 items, item number 1 and item number 6, from 1 to 6. The top section is the correlation, pairwise correlation between items, and the bottom section is the significant level, and at the end here is the determinant. So for the correlation, when item 1 is correlated with item 1, it is perfect correlation. Item 1 correlate with item 2, the value is 0.65, which is within the range. For item 3, within the range. Correlation between item 1 and 4 is very poor, less than 0.3, it is 0.03. So this item number 4 is weakly correlated with item 1, and item 1 and 5 is less than 0.3. So the correlation value between pairwise items need to be examined and checked, and the p-value is given here, should be less than 0.05 for significance, and the determinant have to be greater than 0.40 and 1. The next step is to check the sample size adequacy. So to check sample size adequacy, use the KMO statistics as shown here. The sampling adequacy is given a value in this table, it is 0.6, and the p-value is less than 0.05. So the minimum acceptable score for this test is 0.5. Anything above 0.5 is considered to be enough data or sample size to perform the EFA. The p-value has to be less than 0.05. What is also important that has to be checked and examined is a term called communalities, that is calculated post performing the EFA. Communalities refer to the proportion of variance in each observed variable that can be explained by the factor extracted, or the latent factor extracted. So the value for communalities indicate how much of the variability in the observed variable that can be explained by the extracted factors. The values for communalities ranges from 0 to 1. Higher values indicating more common variance. Higher communalities indicate that a larger proportion of the variability in the observed variable is accounted by the factors, and this suggests better fitting of the model to the data. So variables with low communality may not be well represented by the factors and may need to be excluded from the analysis. So when there is a communality value of less than 0.3, then omit the item and perform the analysis again. Here, as shown, an extract from EFA output analysis. Communality has been calculated at the initial and after extraction for item number 1 to 6. Item number 1, the communality is very high, 0.91, and for item 2 it's 0.47, item 3 is 0.43, item 4 0.96, item 5 and 6 0.3, and so on. So there is no communality less than 0.3. Examining the communality value is essential for performing the EFA. There is another term that has to be checked when performing the EFA, which has to be determined prior to performing the analysis, which is eigenvalues. eigenvalues help to determine the number of factors to retain in the analysis. The value for this indicates the amount of variance explained by each factor. Usually, by default, the eigenvalue is set at a value greater than 1, and the eigenvalues will generate a table, and that need to check the proportion of the total variance explained by the retained factors, and this proportion has to be at least 50% and greater. The eigenvalues can help in optimizing the number of factors and then determining and fixing the number of factors to extract and perform the rerun of the analysis. In the next slide, an extract from the EFA analysis for 6 items has been placed, and a table is generated for the total variance explained. Here we have 6 items and only 2 factors has been extracted, factor number 1 and factor number 2. Factor number 1 can explain 35.9% of the variance, and factor 2 34.1% of the variance, and both of these factors, the accumulative percentage, they can explain 70% of the total variance. So the EFA managed to extract 2 factors out of these 6 items, or sort out these 6 questions or 6 items or 6 variables into 2 major factors, factor number 1 and factor number 2. Both of them can explain 70% of the variances. If we move to the next slide, a plot has been generated. It's called Scree plot and placed in this section here. On the x-axis is the number of the factors that can be extracted, and on the y-axis is the eigenvalue. And since we had set the eigenvalues to be greater than 1, as shown from the Scree plot, there are 2 factors that have been extracted following the certain criteria set for the analysis. Scree plot is a graphical tool to determine the number of factors to retain in EFA. There is another also value that need to examine, which is called factor loading score or value. Factor loading is a correlation between item and a factor. So it is a correlation coefficient between a variable and a factor. So a score will be given or a value, and it's called factor loading. The value shows how much the variable is influenced by the factor. The factor loading value, it is the value that indicates the strength of the relationship between the items and the factors. Larger values indicate stronger association between observed variable and the underlying factor. So factor loading values ranges from -1 to 1. Value close to -1 or 1 indicates a strong correlation. Values close to 0 indicates a weak influence. Positive value indicate positive correlation between variable and a factor. Negative values indicate a negative correlation. So variable with a high loading on a particular factor are considered to be strongly related to that factor and are often used to interpret and label the underlying construct. So factor loading score is an essential values that will help in determining whether the items load into the factors. The higher the value for the factor loading, the stronger the correlation between the variable and the factors, and this will help eventually to identify and label this factor or these construct extracted. The cutoff point for factor loading usually taken is either 0.3 or 0.4 or 0.45, and the way is to delete the items that have no loading or doesn't load into any factors, or have a value of less than 0.3, and then the test has to be rerun. So look for any factors that have at least 3 items with a loading greater than 0.3 or 0.4 or 0.45 and low cross loading. So the cutoff point for the factor loading can be determined, whether it's 0.3. Some researchers prefer 0.3, some researchers make it more stringent and use 0.4, and others even more stringent by using the cutoff of 0.45. Remove any items with cross loading of greater than 75%. Start with one with the lowest absolute maximum loading. So remove the items that have the lowest absolute maximum loading. In the next slide, a table is extracted from an output performing EFA, Exploratory Factor Analysis, with a rotation method oblimin, and the pattern matrix is generated as shown here. There are 6 items, item 1 to item 6, and there are 2 factors that are extracted based on this method, factor 1 and factor 2. Factor 1, there are 3 items that load into that factor, 3 items that measure that factors, item 1, item 2, and item 3. The factor loading value is 0.95 for the first one, 0.68 for the second, and 0.64 for the third items. So all these 3 items have a high score for factor loading, and they all 3 load together into that factor 1. For factor 2, item number 4 and 5 and 6 load into that factor with a factor loading score of 0.98 for item 4, 0.62 for item 6, and 0.57 for item 5. So all these 3 items load into that factor number 2, and the value for factor loading is sufficiently high, and the cutoff point was taken as 0.3, so there is no values below than 0.3. So the factor loading examination or checking in EFA is essential to determine whether to retain or remove item or items from factor or factors that do not load sufficiently into the factor, and they don't have a high factor loading greater than 0.3. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, RStatistic, or Statistics, GraphPad, Prism, GPower, Python, and Mann. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, RStatistics, GraphPad, Prism, Mann, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.